So, hello, Geoff Huston. Thank you very much for joining us today. My name is Jessie Wu, and I'm a reporter with BTW Media. We're currently conducting an interview series called The History of the Internet, speaking with people who played key roles in the Internet's early development. We're very grateful that you've agreed to share your experiences with us, and I'm really looking forward to our conversation today. Thank you for being here. Okay, so the question one is, how did you first become engaged with internet architecture and networking, and what problems were you most focused on solving at that time?
I started my career in computing at the Australian National University in the 1980s. Not many folk are still around since then, but the 1980s was interesting insofar as it was still the age of mainframe computers, but it was also the age of proprietary technology. So, for example, if you had an IBM mainframe on your campus, it's pretty typical that the network you were running was also IBM's SNA network. If you had machines from Digital Equipment, then you were probably running DECnet. Now, the issue is that what if you had a variety of mainframes and wanted users, the members of the campus community with their terminals on their desk to connect to any of these mainframes? Proprietary networks got in the way because only IBM terminals supposedly connected to IBM mainframes and similar. So the industry as a whole, and campuses like mine, were keenly interested in technologies that were, well, vendor independent. We called them open technologies that weren't owned by anyone. Now, there was a long-standing effort in the 1980s, largely sponsored by telephone companies, oddly enough, and European ones at that, called Open Systems Interconnect, which was an effort to actually develop a networking technology that was independent of any particular company. Now, at the same time that this effort was going on, there was an effort within America that had started from a similar premise, funded largely by the Advanced Research Project Agency of the US government, looking at a very similar kind of problem. But unlike the OSI protocol suite, they'd actually developed working solutions by the mid to late 80s, and it was called the Internet, or the ARPANET as we knew it then. So when I was looking at a project to build the campus Ethernet network in the late 1980s, then the choice of networking protocol technology was actually pretty constrained. You either ran IP, the Internet Protocol, or you couldn't interconnect everything. You had to make choices. So I got very, very interested in IP as solving a problem for my campus. Now, about a year later, the entire collection of Australian universities started to look at building a national academic and research network. And again, similar kind of problem. What protocols are we going to support on such a network? Because, without protocols, you don't have communication. Um, I led a charge to actually nominate that the way we should do this is do a core based on the internet protocols as being one which was almost universally supported on most of the computers that we ran inside the academic and research sector. And that kind of got rid of the problem of, do we do DECnet? Do we do PrimeNet? Do we do SNA? Do we do this? Do we do that? It solved it because almost every machine that we could sort of see, there was a port of the Internet protocol available on it. So the whole thing could actually run with IP. So that's how I got into it. After that, it was just a wild ride.
Okay, so I got it. The question two is, in the early days of routing and addressing, what were the biggest technical uncertainties? How close were we to decisions that could have fundamentally constrained today's internet?
That's a very interesting question. And certainly in the late 1980s, there was a big push um, to bring the sort of early internet architecture out of a very, very limited domain of use within a small number of countries into a broader range of use, it was actually accompanied by the rise of the Unix operating system, because Unix was again one of these issues of, if you ran Unix, you weren't locked into any vendor. You could buy almost any computer you want, and if you had a Unix port, then you could run all your software on it without changing anything. It freed us customers from what we called vendor lock-in. So oddly enough, and it's sort of not obvious in retrospect, but the growth of the internet in the late 1980s and early 1990s was explosive. Entire academic and research communities across the Asia Pacific area and across Europe were joining this US-centric IP internet. And even in the US, the academic and research communities were joining in too. What was a quiet, very quiet, advanced research programming about packet networking, by 1990, it was exploding. Now, by exploding, I meant this thing was doubling in size every 6 to 9 months, which, looked at networking technology or any technology, doubling in size every 6 to 9 months is a nightmare. If you leave things go for a week or two, the problem is getting close to being twice as large. Now, the internet's architecture had already gone through a couple of sort of big problems. And one of the early days, long before my time in the early 1980s, was expanding the size of the internet address field from, I think it was 8 bits. Yes, it was 8-bit address fields up to 32 bits. Now, at the time, late 80s, a 32-bit address architecture in network protocol was considered madness. We're talking mainframe computers. And if you took a census of the entire world's computers, and this is before the PC, you'd be lucky to come up with a number of 500,000. 500,000 can be done in 22 bits. You didn't need 32 bits of address field in a networking protocol. And the decision by the IP architects, Bob Kahn and Vint Cerf, to use the 32-bit architecture seemed at the time to be extravagant and mad. But by 1991, we were looking at that 32-bit space, 4 billion possible connected computers, and going, oh, gee, that might not be enough. We're running out. At the same time, also, we were keen, in fact, the entire area was keen, on removing centrality and control. What we wanted were networks, packet switch networks, which were what we called stateless. Stateless insofar as these networks would self-discover how they were connected and automatically put traffic through that network and could repair breaks as they occurred, so that you didn't need to reconfigure the network to disrupt things. You could actually make a reliable chronic connection service on top of what were very, very unreliable components. But again, the issue was, in a small scale, that's fine. But when you're connecting a few hundred new networks every single day, then all of a sudden you start to worry, can my switching devices, can the machines that are performing this routing protocol actually cope with the increasing load? Because previously to this, you have to understand that telephone economics was based on an entirely different model. We were used in the telephone systems to building networks that grew largely in line with population. Population grows 4 to 5% per year, and the network grows about 4 to 5% per year. When you start to double in size every 6 to 9 months, you have a headache. And that headache very quickly becomes, we don't have enough capacity to cope with tomorrow's demand. And so by the early 1990s, the sort of technologists who were regularly meeting the Internet Engineering Task Force, who were taking over the kind of design and vision view from the earlier team that was run by the ARPA people, the Advanced Research Project Agency, the IETF started looking at this problem going, this is serious. We're not sure that the internet's going to survive the next 4 years because we're just growing way faster than we actually have capability. And the major problems that we saw was the capacity of the routing systems, these self-learning systems, and the underlying issue that maybe 32 bits of address space wasn't enough. So there was a lot of work between 1991 and 1994 to try and figure out how to cope with this. And while originally it was an American problem, by the 1990s, with a worldwide engagement from the academic and research communities, it was increasingly seen as well, it's an all of us kind of problem. And even myself from Australia, I was engaged in this area of trying to figure out how to make a network, design a successor network or something that could cope with what we thought was extraordinary growth of the network. At the same time, computers were getting smaller and faster and cheaper. The mainframe was slowly disappearing, and instead of spending tens of millions of dollars to buy the next computer, you went down to the local store and bought a Dell PC for under $1,000. All of a sudden, we were connecting up literally thousands of these small computers all the time. So that scaling issue was very, very real, and the problems were very, very, very fundamental. So decisions were made. We actually designed a successor network protocol, IP version 6. The routing one, not so easy. And rather than actually building a new routing protocol, we mucked around a little bit with the so-called addressing plan. And instead of having a fixed boundary between the network part and the local interface part, we made that variable. We made it so you could accommodate big networks, little networks, medium-sized networks, all in the one addressing plan. That approach, what we called classless interdomain routing, has actually managed to work for all of the last 40 years and continues to work. So oddly enough, we didn't change the routing protocol. We made a subtle change to the address architecture.
Okay, it's striking that how small decision choices could have enormous long-term consequences. So the question three is, was there a moment when you realized the internet would become something truly global and transformative?
That's an interesting question. And I suppose there were two answers. A lot of us who were engaged in that work were true believers. We really thought that the phenomenal work that had gone into the open systems interconnect architecture was wasted effort, that they were designing something that actually wasn't viable and in some ways never stood a hope. The reason why, it was still paperwork, it was still mired in some very, very deep political decisions that caused internal contradictions. It was one of the few network protocol suites that was so internally contradictory that if you chose one profile for one computer and a subtly different profile for another computer, they couldn't talk to each other. That does not seem to me to be a connected network. However, this was still an experiment. It wasn't commercial. No one was making money. This was really something that solved a problem for academic and research communities. And beyond that, we were horrified by the idea that this would become a commercial offering and that folk would pay for it. That was never part of the story. However, there was no other plan. And by the, I suppose, mid 1990s, it was pretty clear that there was no alternative, that folk were buying desktop computers, home computers. Computing had become a consumer item. But the whole issue of trying to create a network to support all those computers in all those homes, the only choice was actually the IP protocol. And it wasn't a deliberate thing. It was just there was nothing else. The early efforts commercially to do this in what we called walled gardens, and there are a few of these bulletin board systems that sort of lingered about, were really so dysfunctional But by the time a real networking architecture came along, it just was so attractive that folks just scrambled onto it. And so we didn't decide it. It was just what we thought would be the successor protocol when the adults moved in never happened. And we ended up inheriting the entire global communications load without ever actually asking for it or even claiming it. It was just we were the only ones left in the room. Now, if you think about the original design choices that allowed that to happen, part of the issue was, and I think it was an outstanding piece of work, is that the IP protocol architecture was largely the result of two people, Vint Cerf and Bob Kahn. Design by committee is a disaster. We've seen it in computer languages, we've seen it in a whole bunch of technologies. Committees make shocking decisions. They're internally inconsistent, they constantly seek the middle ground, they can't make tough choices. If it's a choice of A or B, typically committees try to have A and B, even if they can't coexist. Committee programming languages that died a death include PL1, nobody knows. These things never stood a chance. Unix was so brilliant because it came out of the minds of basically two or three people. The C language, one person. Part of the beauty about those kinds of highly focused technologies is that if you understand the design thoughts of the person who actually built it, you understand the language. It's easy, it's consistent, you can do incredible things. Committees tend to create complexity. Complexity is the enemy of actually creating usable technology. So those early design choices by Vint Cerf and Bob Kahn, minimalism, don't solve everything, solve only just enough and leave everything else to someone else, were, I think, phenomenally far-sighted decisions about doing as little as possible, as gently as possible. And it served us well for nigh on 50 odd years now.
Okay, I got it. And as global growth accelerates, some early architecture assumptions begin to reach their limits. And that's question four. Why has the transition to IPv6 taken so long? And what does this tell us about large-scale technological change?
The entire internet's computing revolution has actually ridden a more fundamental revolution in silicon chip manufacturing technology, which we often call Moore's Law. That since the original invention of the integrated circuit in the late 1950s, engineers building these integrated circuit fabrication plants have been able to double the number of gates on a silicon chip at the same cost per chip every 2 years. So what's actually happened is every 2 years, computing got twice as fast, but cost per unit of computing less than half every 2 years. So what was going on was that the computers were getting more powerful and cheaper and smaller, and they were getting more prevalent. Now, this is the precise opposite of the technology model of the predecessor of the internet, the telephone network, which had very, very simple, dumb devices, a speaker and a microphone, and all the intelligence was placed into the network. So the network actually carried the money, it carried the importance, it carried all this weight of investment, and the edge devices were basically useless appendages. Once you get a huge amount of computing capacity attached to the edge of the network, they have more processing capability than the network could ever dream of. There are millions, hundreds of millions of computers and one network. And so all of a sudden, you can do a whole lot of work at the edge you didn't need to do in the middle. Now, the first designs of the internet were, I think, strongly influenced by a telephone-based model of connectivity and technology, that the network was still trying to do a fair deal of work, and it was trying to relieve the processing power on end systems. It was trying to make the connected computers relatively simple. And so the whole idea of an address-based network, where every device had a consistent and permanent address, was, I think, a throwback to mainframe thinking of the 1970s. When we really started to scale up scale up technology, we very quickly realized that the most scalable model was to actually make the network asymmetric, different. There were servers and there were clients. At home, at work, people had clients. My mobile phone is a client. My watch is a client. It doesn't serve, it actually uses services. Now, a client doesn't need its own address permanently. I don't need to get in touch with a client. Clients get in touch with servers. And when you look at the network from that perspective of client-server architectures, you very quickly realize that addresses are not the fundamental language of a network. Not anymore. Addresses are merely temporal tokens to stop packets getting confused. So all I've got to do when I want to make a conversation as a client is borrow a unique address, use it for the length of my transaction, and then throw it back into the pool, because after I've used it, I have no further need. And we've actually subtly changed the internet without even noticing it into a network that is actually based on a naming system. It's domain names that matter. Now, scaling addresses is hard. Unique addressing is hard. Scaling that to 30, 40, 100 billion devices, a trillion devices, is a nightmare. No matter how you try and do it, it's expensive. Let's not bother. Let's just walk away from all of that and instead name the servers. Not give them addresses, but name them. So names are important these days for scaling. Addresses are just a convenience at a network level. They don't actually need to be unique. They're quite ephemeral in some ways. And that has been the key to almost unconsciously building a network that handles 30 to 50 billion connected devices today. And we're confident we can grow that tenfold or even 100-fold without changing the fundamental architecture. So that was the big key. We're using the power at the edge, not trying to scale the middle.
So these challenges naturally raise deeper question about how the internet is governed. So that's the question 5. How has internet governance evolved, like in the roles of RAIs, standards bodies, and governments?
Those standards bodies and governments are living a reality that's about 3 to 4 decades too old. When we were in the telephone system, the actual network was hideously expensive, really expensive, and complex to run. So complex that in most countries, with I think the exceptions of Canada and the United States, they were run by governments. They were centrally coordinated. They had all kinds of contracts about standards, about modes of operation. And in essence, what they were doing was safeguarding what was a national investment. Who was funding it? Well, governments were. Yes, they made a profit, generally, unless they were really poorly run, like France Telecom. Yes, they made a profit, but nevertheless, it was a public undertaking. But the issue with computing was that the government didn't own the computers. The government didn't own, what's in my hand, what's on my wrist. The government doesn't own my devices. And if the bulk of the intelligence and functionality of a network is left to me as a consumer, how should the network service me? Surely that's my choice. That's my money. And this, what we call deregulation, which was a wave that started in the 1970s, oddly enough in the United States, when the Department of Justice put out an antitrust suit against AT&T. But the outcome was that telephone companies worldwide were floated on the private market. No longer did they demand public capital to make a bigger telephone network. They were companies like every other company. They made their money from selling services, and they had to adjust and adapt to what users wanted. So let's talk then about the governance of that system. How does it work? Well, I would actually argue it works like any other system based around a user commodity. It's markets. Build something that people want, they'll pay you money. And as long as your business model can actually produce that at a profit, you're fine. Build something that people don't want, you can't sell it, it's not going anywhere. So in the long term, governance is actually all about what you and I as consumers are willing to pay for. Now, that has some very unfortunate side effects, which many people worry about, and rightly so. In this kind of technology world, volume creates very low cost. If I'm 10 times as big as you in producing a good, I can put that good on the market at such a cheap price and still make a profit that you're unable to compete. Big gets bigger, small has a problem. Now, that's been sort of the sustaining issue with the internet and its governance. It's really just a reaction to what consumers want. And what consumers want is more for less. And so what's done in response is that we've actually created bigger and bigger and bigger service providers who can actually produce these services at phenomenally low cost. Take, for example, the simple search engine. You're mining most of the world's information that we've collected over the last few decades. And every time you type in a search query in your favorite language, you're executing a search that would take an army of researchers a few months to do. 20 years ago, 50 years ago, that would have cost millions of dollars. It costs the search engines about 3 cents, possibly less. And 3 cents is low enough that online advertising can fund it. And so most of the network and its services are actually free to users. And the funding model is based on advertising because the incremental cost of these operations are so low, but the benefit high enough that we're all hooked on this. It's just so seductively useful, so cheap, and so functional. Now, that's governance for you through markets. It's a function that says if you're doing something that folk want at a price and functional level that is popular, you will reap rewards from that activity. If you've missed the target, you cannot expect anyone to subsidize you. There's no cross subsidies going on here. It is market-based economics. So a lot of folk who kind of lived and loved in the telephone network go, oh my God, what's going on? This is terrible. And folk, I suppose, like me, who are going just after that, go, well, we're deregulated. This is a standard market. The internet's nothing special. It's just pandering to what people want. As long as we do that, we're okay. And that's all we need to do.
All right, that's lead to our question 6. Is today's increasing centralization a threat to internet resilience or an inevitable outcome of scale?
That's a very, very interesting question. And in some ways, it is both. You see, if you wanted resilience by having a whole set of alternatives, that if something fails, there's always another, then you do that by making sure that no single player gets too big. And some markets actually do that in some ways, that there's always a competitive pressure so that no single player takes over and creates a monopoly and things distort and you get fragility. That's a standard sort of mechanism. But that has actually only happened on the internet because of just one thing. Moore's law, that doubling of the chip size every 2 years, reducing of cost, is a very, very harsh taskmaster. I buy a bunch of computers, a data center. I set up my service. You, my competitor, wait for 2 years and do the same thing. You're going to do it at half the cost that I have. Half the cost. What am I meant to do? Constantly, I'm under pressure because new entrants in the market come in cheaper. They might be smaller, but Moore's law has given them advantage that overcomes their smallness because their access to new technology gives them so much more efficient technology that they become cost competitive. So as long as Moore's law was working its magic in the chip level, as long as the costs of technology were coming down, this thing had a sort of a metastable balance that the big folk were constantly under pressure from nothing more and nothing less than the future. And in order to secure their position, they had to constantly battle with new market entrants trying to refresh and upgrade their existing base. So the real question is, will Moore's law continue to give? Will we make chips ever smaller, ever cheaper? And the growing prospect now in 2026 is no. We're down at scales that are very close to atomic. We're pushing our manufacturing processes to an extraordinary degree, and it is unclear that the good folk at AMSL making next year's chip fabrication plants can actually do the magic and make them make the cost of processing half again. And if they can't, then all of a sudden the future is not at risk. Once you get to the point where Moore's law no longer functions, the giants remain giants. The future is not a competitive threat. And then you get the next phase, which is most of the downsides of a small number of very, very large players that dominate the world market. Right now, we know who they are. They're the very, very large companies with trillion-dollar valuations, the Amazons, the Microsofts, the Apples and the Googles of this world. I mentioned NVIDIA, but I'm not sure NVIDIA's entrenched. I think they're still vulnerable. But the others certainly at a point where once Moore's law stops threatening their future, they're in a very different position. And at that point, we are going to have to come to terms with a number of private sector companies who are bigger than any single government, bigger even than regional governments, who have pushed things so far that the existing social laws and conventions are getting stressed, that employment is not what it used to be, that our lives are not what they used to be, that the way we interact, the way we work, the way we generate value in society are being changed in ways that we only dimly understand why. And the controlling function is all about the exploitation of a few digital behemoths. This is not stable. This will not end well. There are a whole bunch of challenges inside this. And it was actually a philosopher, a Canadian philosopher, John Ralston Saul, that said, never ever expect a private company to act in the public interest. It's not their job. And the task before our governments is a very, very hard task, which is actually to try and protect our societies from ruthless exploitation from these same digital behemoths. That Moore's law kept that in check for so many years that it wasn't really a problem. But I think now it is a problem. And it's going to demand the skill, the imagination, and I think the courage of governments to take that agenda on and advocate for the interests of us, the humans, inside this environment. So it's a big topic, and there's much to be said in the future on this.
Okay, so this which brings us to the future and to those now shaping what comes next. And that's our last question. What lessons from the internet's early history should engineers and policymakers be careful not to forget?
For policymakers in particular, applying what we learned last year to what will happen tomorrow is never going to end well. Never. Humans may like consistency. They like patterns. They like things being the same. But the technology shift is to constantly change the tables, to change everything. We don't understand where we're going with artificial intelligence. We really don't. But we do understand the power of pattern matching. The power of some of these computing algorithms are incredible. And coming to terms with that is going to prove to be an exceptionally difficult challenge. What does it mean Say when I'm a code developer, when AI can do a better job for a lot less money? What does it mean for a radiation oncologist looking at x-rays when an AI engine can do a better job than me? What does it mean even for lawyers and the legal system when an AI system can do a better job? We don't understand this, but we're absolutely going at full pace, developing these systems fueled by a phenomenal amount of venture capital money. The venture capitalists are not trying to build a new society. They're just trying to make a lot of money very, very quickly. And by the look of it, they might do so. But once they do that and capture all this value, how does our society function? Now, you say it's an engineering and a policy making question. I actually think it's an us question. No matter who you are, no matter what you do, no matter how you do it, our lives will be changed. And I certainly look at, the next generation, my kids, my grandkids, and go, well, their life will not be like mine, not in the slightest. But I can't tell what it will be like. A lot of the things we're doing now, I assume you're a human at the other end of this connection. In 10 years' time, that's debatable. And equally, you might say the same about me, that I could just be an auto robot, Geoff, saying the same stuff, and it probably would be, a valid scenario. What does that mean? What is value? What is interaction across this network when there's another player of synthetic programming that reproduces patterns in ways that we never envisaged as humans? So this is much bigger than an engineering problem, and it's much, much bigger than a networking problem. I also think it's causing challenges in policy, but it's more than that. It's causing challenges to government. It's causing challenges to the way we structure our lives in societies. What makes societies stable? What makes societies work in the interests of the people of which it's formed? How do we deliver cost-effective health, education, and so on in these new worlds? None of us want to give everything to a handful of billionaires. That's just crazy. But that's what we've done for the last 10 years. And we should stop. We should try something else that dishes out these benefits to the other, 7.99 billion of us on this planet, to actually manage that we all get some of the benefits from this astounding, bountiful world, of the digital economy, rather than just hand it all to 3 or 4 people who hopefully will send themselves off to Mars and disappear.
It has been truly wonderful to hear your perspective. Your work has had a lasting impact on the internet and on generations of engineers, and it means a great deal to us to be able to share your insight with our audience. So thank you again for joining us. It has been a real pleasure speaking with you.
Thank you very much. Thank you.